Today on the show, we have Eric Reiter, who is a garage experimentalist, and I don't say that to demean him at all. He has a wicked cool setup with all sorts of fantastic radiation devices and oscilloscopes and beam splitters. And he is attacking the concept of the discrete photon.
He calls it the unquantum effect, where he can show that the wave-particle duality of the photon, the electron, and even the helium atom is really a defect of measurement. And it's not spooky, it's not weird, it's just a threshold resonance effect.
And this is in line with the way that we've been starting to talk about the atom on our show and over at our other channel, The Material World. So it was really fun to try out our ideas with Eric and really just see so much enthusiasm for something so fundamental.
He's incredibly passionate. He's incredibly well-versed in the historical literature. He knows his entire library of physics history, past and present. And we think you're gonna love it. Absolutely, no questions asked. And thank you so much to Eric Reiter for spending this amount of time with us.
And thank you to the patrons for bringing us Eric Reiter in the first place.
Yeah,
it's actually
thanks,
one of our patrons, Neil, who brought him to our attention. And thanks to the rest of the patrons, really, for just supporting this project. As you can see, we are slowly constructing a new studio around us, which is going to hopefully allow us to automate a lot of the editing and get these releases out quicker. So that couldn't have happened without you guys. If you want to join up and become a patron, hang out with us on Sundays, that would be really cool. If you don't have the bread to support us, just share the episode with somebody you think will enjoy it.
And in the meantime, enjoy Eric Reiter. We'll see you soon.
The scientific revolution starts now.
Let us see in the dark.
This might be a good point to give people like a very brief overview of what it is that we're going to get into. So in as brief as possible of a space, because we're going to spend the next, 2 hours talking about it, if not more, can you give us a summary of what it is that you found?
Yeah, right. That's kind of what I'm getting into. It's about the definition of the photon, essentially, realized into an experiment. If you go to several famous books like here's Atomic Physics and Human Knowledge by Niels Bohr, you can read a quote out of it. And so I'm going to read what Einstein says is a definition of a photon. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction of propagation, the photon may either be recorded on one and only one of two photographic plates situated at great distances in two directions in question. Or else we may, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. All right, let me actualize that. So they're saying the definition of a photon. Now, people will have different definitions, and this applies for like electrons and neutrons, all that stuff. So whatever it is, if it goes with a detection click, and this is a beam splitter, like a half silvered mirror. And so there's two detectors, a detector and the source, and it goes this way. And so by quantum mechanics and the model of the photon, if it's supposed to only show up one place or the other, okay? It's not supposed to go both ways because that's the particle property of the photon. And all of these quantum mechanical particles. Now, but if you were to reconverge the beam with the same source, to put a mirror here and another mirror here and put it together, and then look over time, you'd get an interference pattern where you go click, 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 and you'd get a a pattern that could only be described by waves. So this is the wave property, and before I showed the particle property. Now the wave property and the particle property are mutually exclusive. Straight away from this definition, which is a description of a model of what the photon should be. So it's important to understand the background of where quantum, this is the model of quantum mechanics.
Sure.
And it's straight away pretty nutty because it's about a contradiction where if it was to be able to go one way or the other, then if you try to make it go both ways, well, you just found it went one way or the other. Now it has to go both ways.
Right.
See?
This is why people think quantum is so spooky and magical, because it's the scientific observation of a contradiction.
That's right.
But there's a difference is there a difference in the detection method that's used when they detect as a particle versus when they detect as a wave?
No. Now you could use the same detection mechanism. You can have a photomultiplier tube for the one way or the other, PMT, and it'll go click. And then when you do waves, if you want to, I should draw it I should just draw it separately. Okay. You take the PMT and you scan it across, and the same detector, and it'll make a pattern. It'll be a lot, and a few, and a lot as you scan it over the interference plane, the place where the light will converge. So it's the same detection mechanism. It's just a matter of whether you go over time to get more clicks after you converge the beam. So yeah, it's a direct contradiction. So what I do is I go and say, look, there must have been some mistake in this experiment. And I redo this experiment and I analyze other people who did this experiment. I found the errors in their ways. And when I do the experiment, I do it with gamma rays, and I get the opposite result. And I also do it with atoms, which no one has attempted at all, because it's like blasphemy to even try. But I did it.
When you say you get the opposite result, well, first of all, there's a lot to unpack there. So directing gamma rays is no small task.
Yeah, let's get back to the gamma rays. Let's figure out the questions.
Yeah. Right.
But also you're saying that you see a different result.
Right.
Which I assume, what is the different result you see? No interference patterns, or what do you see?
On this experiment, it's a coincidence experiment. So I'm going to explain the coincidence experiment, where the detectors make clicks, and it's about looking at the time sense of how these clicks show up. And I do the experiment with the same kind of electronics and equations that they do. One thing you have to figure out is that you have a source that emits one at a time in order to do this experiment. And when you do that, it's a similar coincidence experiment. So let me explain that one first, and then I'll get to this coincidence, and I'll show you how everything works. So when you set up a source, well, the way I do it is a little different from the way they do it. I do it
who are these people, by the way?
The people who won the Nobel Prize recently.
They do this exact experiment
with light. Mm-hmm. Clauser and Aspey did the same beam split experiment to see if it goes one way or the other. They do it with visible light. And it's been done by several other people also. But it's only been done with visible light. No one else has tried gamma rays because it's thought, I don't know why.
The gamma rays are more difficult to reflect. It depends on the angle, right? Like you can only reflect them at glancing angles or something. Yeah,
I go through all that. It does reflect. They can get them to reflect, so I've done it with reflecting beam splitters. I've done it with a beam split geometry but I found a better geometry that does a beam split, which is where it goes through one detector and the other. But first you have to understand what it means to have one at a time to do this test right. So in nuclear physics, they do the test to see that it's one at a time. They do it with gamma rays, and it's very well understood, and everybody agrees. I agree. So you start with a source in the middle, and you have a detector on one side and the other, and it goes through to a coincidence gate circuit. And if it goes to both, you can tell that it emitted two at a time. So what they do is that you put together a graph of time where zero difference in time is in nanoseconds. So it can go, if it's a source that is two at a time, it'll go click, 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 click. It'll make a peak in this histogram of the difference in time that the clicks show up. And then you know it's two at a time. But what we want is only one at a time. So that histogram, what that shows up, it makes a graph that just looks like noise. There'd be click, 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 click. So this vertical is like the number of clicks, the click rate. And it's like plus time, it'll be minus time and plus time in nanoseconds. So these clicks are looked at that way. And I have videos just to show just how I did the experiment. All the details are on my website. But it's
basically you have a detector that's set up equidistant from some emission site, and it's able to say whether some impulse arrived at it coincidentally, or whether there was some discrepancy between the arrival at that source.
It looks like there's two detectors. Is it the same detector or is it two detectors?
There's two detectors.
But they work together to make this coincidence noting system.
There's two separate detectors. Right? They go to this will make a pulse.
So it seems like their distance, like the distance at which they're fixed would make an enormous difference.
No. The speed of light is way too fast to care about it.
Even in terms of phase. Because you're talking about phase interference, right? At some point.
No, it's just timing.
Just timing.
It's just the time between clicks. And so it's a nanosecond.
As far as I can understand, this setup is not yet the experimental setup. This setup is a source checking setup to make sure that it's actually emitting one pulse at a time as opposed to two pulses. And so we're not at the point of interference patterns yet. At this point, it's literally just number of detection events per unit time.
I'm not testing the interference pattern component of the definition of the photon. I'm testing the one way or the other aspect of the definition of the photon. So, but I do this test also with so using the same electronics and the same detectors, then you rearrange the detectors with the source, and then the better way that I do it is where you have a thin detector and then a thick detector, and you look at the time between it. Now, I've done it where it looks like a beam splitter and different geometries, and they both work, but this works best. So if it was a photon, it should go to like one detector, and then there could be some that passes through, and then it could go to the other detector. But the model of quantum mechanics says it should just go to one or the other, just like that. Now, I see it going to both, and what I do is compare to chance. And this comparison to chance is the same thing about whether there's a peak in this histogram or not. So they both say the same thing. You could either look at the shape of this graph, or you just use the chance equation. And I've tested this chance equation. So it's easy to find chance. So that's just about the only equation I use. The chance equation, this is really important. The rate, so everything I do is simple. The rate of chance is equal to the rate of this detector and the rate times the time window through which you're going to count coincidences. And so we use a symbol here of tau. So that's how you get the chance rate. And other people do this when they do this experiment. They compare to chance. And you'll see it in a few other papers. And you'll see it in the work of Clauser, who I mentioned won the Nobel Prize for this. And Clauser got just noise in this graph. He shows the graph. Okay, so he does not see anything. He sees chance. He only sees chance. I'm the only one to defy chance in this kind of experiment by seeing a big peak here. And then when you calculate it out.
And what's the only difference is the wavelength?
No.
Okay, so what are you doing differently?
I am using different kinds of detectors. I have to use gamma ray detectors instead of visible light detectors.
Okay. Isn't that just changing the wavelength?
Yeah, it is. But there's other things that are different, like the detectors, and that's pretty much it. The detectors and the source.
So you're looking at a different wavelength.
Yeah.
And what is it about gamma rays that changes the system?
Right. Plenty.
Yeah. Plenty. All right, let's do it.
I know about all that.
Yeah, we don't. That's why we're here.
So, there are problems with the photomultiplier tube, and
that's the detector that Clauser is using.
The detector that they use for visible light.
So Clauser would be using the photomultiplier tube.
That's right.
Okay. And so what are the problems with it?
Well, for one thing, many physicists will say that all the pulses are the same, and they're not. If you go to Feynman's book, he'll come right out and say that the pulses are they're just all the same, but they're just not. There's a wide distribution. So if you look at a graph of the pulse height versus how many, there's a wide distribution.
What are these pulse things? This is in your laser beam?
Graph. It's a graph. So the photomultiplier tube and the gamma ray detectors, all of these detectors will make pulses, and there'll be different size pulses. So if you look on a time graph on an oscilloscope, a photomultiplier will have a pulse that's so big, but it'll have smaller pulses and larger pulses.
And this is a signal per time is what this pulse is, right?
No.
The one at a time business is just looking at a lot of these, and you'll see pulse over time. And you'll see that there's separate pulses, and they don't overlap each other so much that it just makes a DC. So you can see if there's one photon at a time just on the oscilloscope, and it just makes pulses randomly in time as you read over time. But each separate pulse has a characteristic which is really important. The pulse height is proportional to the frequency and proportional to what they call the photon energy. But it's not accurate. It's not perfect. This is a very rough image as to what's going on. There's a wide distribution of the height versus the number of pulses that happen. So if you look at it with monochromatic light, one color, there's still a wide distribution as to how big the pulses are.
And so you're basically saying that if you maintain the frequency of your emitter, you still get a distribution of heights of the waves.
That's right. Of what they call the signature of the photon.
No, literally frequency. right? You have one wavelength of light.
Is that
Yes.
is that possible to generate one wavelength of light?
Doesn't a laser do
It's
that?
not really one wavelength. You get so narrow that it doesn't matter.
Okay.
So they put it through spectrums and stuff. But for monochromatic light, and I've done that experiment, by the way, by putting light sources into photomultipliers to see this distribution of pulse height. And the problem with the photomultiplier tubes and the way everybody else uses it is they have to decide at what height they're going to use to count the photons. They set, actually,
They set a baseline. They're basically like, above this is considered a detection event, since it's a voltage, they're like, above this voltage we count detection, below this voltage we don't count detection.
that's right.
Hence the threshold model.
Hence the threshold
Well,
model,
it's a different threshold. But yeah, it's a threshold, and they set it, but they don't tell you how they set it. And they don't do any discussion of this distribution of the photomultiplier tube. And there's a real problem with that. And it's harder to explain, but I'll just try to say it briefly, that if you set this lower level too low, you favor my experiment. If you set it too high, you favor their experiment. So there's no way to do it with a photomultiplier tube.
Are they trying to set it to match the Planck scale? Is that perhaps why they're dialing into?
No, the Planck scale is some other thing altogether.
Well, no. What I mean is
they're setting it so that they read it like quantum mechanics.
Right. So that means that the energy is equal to the Planck constant times the speed of light over the wavelength. So if they know the wavelength, they know the energy that they're emitting, then they can back calculate the threshold that they'll need to dial that in, essentially.
Oh, well,
Like if
yes,
you can essentially figure out how much it should be.
They don't do it that way in practice because there's so many variations in how you set the photomultiplier tube and all the electronics along the way. The way it's done, I don't know how they do it. They don't say. They don't say how they set this lower level. I can tell you how I do it.
My guess
And
is you can
very
predict
simple.
you can predict how much energy it should be, and you could back calculate the threshold from that. But it does depend on that, like a priori assumption that
They'll look at a distribution of pulse heights. They don't have to know the energy. They'll just look and say, "Oh, we have a lot of them here. Let's just set it so we see a lot of them."
well, they know how much energy that they should be receiving at the detector. They know how much each one of those photons should be carrying at a given wavelength. And so they could back calculate the threshold from that.
It's too hard to do, to figure out how big should a photomultiplier pulse be, because it's a function of everything about all the chemistry in the thing and the voltage you put on it and the gain of the amplifiers and a bunch of other things.
You're basically saying that it's not the material of the system that you've built changes it. Like if you change the length of a wire by a few millimeters, you're going to change the way that the oscilloscope is reading the height because you're changing the electrical properties of the system.
It turns out that the length of the wire doesn't matter because I'm dealing with times that are on the order of microseconds, and changing the length of the wire is going to change it by nanoseconds. So it doesn't matter.
Mm.
My point is that there must be a calibration component to this system where
they know how much energy of a photon should be there with that frequency of light.
There you go.
They know what it should be. But like to then calculate how big should the pulse be is a much more complicated thing. They just look at the distribution of the pulses and they say, oh, a lot of them are here, and that's the pulses we should measure. And that's pretty straightforward. The problem is they don't
each one of these pulses is supposed to be a photon, right?
Yeah.
Right. So that they can easily know exactly how many photons they should expect from that simple
No.
relationship.
Well,
Because the photons their energy is quantized, so you should be able to figure it out. If you know the power that you're receiving, you should be able to do
the rate
calibration
of pulses is about the power, but each individual pulse is about the photon energy. So there's two different things you're
but the
talking
energies
about.
have to be conserved, right? So you could
Energy is conserved.
you could figure out how many photons worth of energy you had there.
Yeah, but we're not doing that yet. We're just looking at pulses and saying, how big are the pulses, and
Right.
how are they distributed in bigness?
I'm just trying to understand
pulses.
why the academics, how they came up with their scaling system, and I imagine that it's back calculated from the theory essentially.
Well,
what does that look for?
That I can't help you.
Oh, okay.
Sorry.
the problem is that people see these pulses on the detector and they assume a photon hit there, and that's a false assumption. That's what we're trying to show is not true.
What do you suppose happened?
That the model of the photon breaks down in my experiment, that it does not go one way or the other. There's something else that's happening, which is an accumulation hypothesis. And so I'd like to explain what this accumulation is in a simple way, which is, and I do it with cups. It's the threshold model.
Before we move to the accumulation, I just want to have a single sentence summary of this entire discussion to make sure that we understand. Right? Well, no, because I mean, I think that it's complex. There's a lot of ideas in the air. And if we move on without having it digested down into a piece that we can carry with us, it's going to make everything else go down strangely. So if I understand correctly, what you're saying is that they arbitrarily, in the academic experiment, are setting a threshold for what they are registering as a photon event on their oscilloscope, and that threshold, when you change where it's set, you get a different measurement. But the measurement is of what? Is of the number of photons that are being
Yes,
released?
it is. You'll change the number.
Okay.
You'll change the count rate, and you'll change the sense of what's a coincidence or not. You'll let through more pulses to make coincidences one way, and you'll inhibit coincident pulses if you set it the other way.
So if you set it to be a tighter threshold like they do in the academic model, you are discounting a lot of smaller pulses, and so you don't see the coincidences of them hitting the two detectors at the same time.
Right. That's it.
But if you set it at a lower point, what's happening is that you are seeing the events the way that you would expect to see them at both detectors.
That's right.
Okay.
So that's only one of the problems that these experimentalists are ignoring, because they don't talk about it. And it's plain to see that photomultipliers have this wide distribution of pulse heights. And furthermore, they just talk about it, that it's photons anyway. And people like Feynman will say that there is no pulse height distribution, and on and on. But there are other problems. But let's go on.
Hold on. One last wrap up. If you are getting detections at both places at once, that immediately unweirds the quantum.
Right.
What they're saying is that you only get the interference pattern when you change the way that you've set up your system because something spooky is happening. But what you're saying is that the reason that you don't see it at both detectors in order to generate the interference pattern in the first configuration is because their threshold is too high, and so they're not seeing the smaller pulses that are actually in both places.
Yeah, that's pretty much it.
Okay. All right, let's move on.
Yeah. I'm not really sure if they're going to see it that way, because I've not done that experiment. But I know that it's something to be addressed. as to how they set it. And amongst all the other kinds of problems with doing this experiment, that's the main one that I point out. But you see, gamma rays does not have that problem. That's why I went to gamma rays. I avoid the distribution of pulse heights for the gamma rays is like that. So you're able to look at these pulses in terms of both energy and time to make the argument that you're getting 2 for 1. It's a 2 for 1 experiment. It says that if you think that it's photons, we're going to violate energy conservation, and you're going to just say Eric is crazy because I'm getting 2 of them that are big pulses where I started with 1. Okay, that's why nobody else did it. But I can explain how it can happen because it's not quantized. I'm saying that there's an alternative to quantization, which is the thresholds model. Now, it turns out the threshold model is old. Planck worked on it. It's Planck's second theory, and I expanded on it. And then Sommerfeld and Debye and Millikan explored this idea of whether things can load up. Now, let me explain the loading theory. The loading and the threshold is like cups, okay? I'm going to have a full cup here, and I'm going to throw it at these 2 cups, but these 2 cups are partially filled, but you don't know it. You don't get to see the partial fillness. The rule is when it gets to the top, then it all spills over. So you have atoms or whatever they are, you start with a full one, and it'll emit a whole H nu worth of energy, and it'll go splatter, and then it'll go full and splat, and you get 2. So it's a 2 for 1 effect. It's a trick that I figured out how to see through the illusion of quantum mechanics.
Interesting. and that has something to do with the baseline state of the atoms that you're interacting with inside of the detector.
Yeah. In the atoms or electrons or whatever's going on in the detectors loads up classical energy to a threshold. Planck's constant times frequency is the threshold. So it's saying that Planck's constant is a maximum, and that the equations are pretty much true, but you have a different wording around most of the equations to get rid of the ghosts.
Are you satisfied with this so far? Like in terms of your questions?
Yeah, I mean, clearly this analogy, the liquid, means some sort of impulse that's being loaded onto the atoms structurally, like some sort of tension or something is being applied to them and then released in a cyclic fashion, which is quite fascinating to think about.
Yeah, it's a resonant absorption. So it's frequency resonant absorption atom cups that will build up when it reaches kinetic energy, when the electron kinetic energy reaches threshold, Planck's constant times frequency, then it can give up all of it to some other detector like the photomultiplier tube. And it'll look like a photon hit there, but it was that it reached the threshold of what was inside to give that click.
Well, what's really interesting is that the thresholds, these energy states that the atomic shells, the electron shells take on, they're really different structures at some point, like each one of these orbitals has a different, they're called variably orbitals or energy states, but orbital is a more material way of thinking about it. But when you snap from one structure to the next, there's a lot of loose motion in the system that is taken up as slack, which we perceive as these waves or these, I guess as pulses.
They call them quantum leaps or quantum jumps. When it jumps from one level to another, magically just jump from one. So I'm explaining how it can go from one to another. I'm saying that it goes gradually, but you don't see this gradualness. You only see when it reaches the top, and then maybe there'll be some detection event like it'll make a different frequency of light when it does that.
Right, right. Well, it's interesting because if you've ever seen those, I'm blanking on the name of it, but people will have these cymatic demonstrations.
Chladni.
Yeah.
What is it?
Chladni plate.
Chladni plates, yeah. And you pour the sand onto it, and at certain frequencies, it's too chaotic, and there's not really a transitional structure that can be measured. You're not seeing anything that has any stability.
Right.
And
That's
so,
right.
yeah, it makes a lot of sense.
You can see the threshold. I saw the threshold model in the musical instruments that I built. When I put a feedback on the musical string on my creation, it was the sun harp. The sun harp, I had it on display in the Exploratorium. When you load up the energy of the musical string, it gets bigger and bigger, but then it can't hold anymore, and it goes to the next harmonic. So music told me about the threshold effect.
Yeah, only certain structures are stable, resonant structures, and they burst between extremes very quickly. And I think that is the right way to be thinking about light. I actually am kind of shocked that anybody thinks about it any other way. Like it's hard to imagine as anything else other than a something structurally resonant within the system. I mean, the problem is we don't have a material conception of the medium which binds the atoms to one another. And so people have really escaped thinking about these resonances in terms of the way we think about all other resonance in physics, right? Which is impulse exchange between networked entities or it's just hard to imagine how far it's gotten off the rails.
Well, I did some work on that. It's about the nature of charge. My work is really a theory of the electron. And I derived the photoelectric effect with waves I looked a lot for the derivation of the photoelectric effect, and everybody else kind of falls short. And usually they say Einstein did it, but it was such a simple thing he did where he said, Planck says, actually he derived E equals h nu or whatever. So, oh gosh.
I pulled up a photograph of your solar harp.
Oh, good.
It's it's built out of the jawbone of a whale?
Right.
What an
this is pretty beautiful
instrument. It's stunning. It looks like something out of a Mucha painting. I want everyone
I was
I'll put
19.
a link to it in the description.
Good. I did that at age 19. And there were many serendipitous events to the story of how that came about. And so the experiments and what happened with the sun harp, the way it illuminated one spot, then it was able to make different shapes as the string wagged around. And then there were how difference frequencies worked and the threshold. So all three of those ideas I later incorporated into the physics.
I think that's often the path for the people who advance science are often the ones that have some kind of other background where they're able to integrate the ideas that they see at play in the world and understand that they must be operating at some more fundamental level than just the macro scale that we're capable of interacting with. You're kind of talking about this.
All the original physicists were way into these ideas. I mean, they saw music amongst the orbits of the planets, and of course there are perfect resonances throughout the solar system.
Aren't a couple of the orbit periods perfect fifths?
I mean, there's let's see, Venus and Earth have a perfect fifth. There's octaves in several of the moon systems, and resonance. The sound resonance that we put together and call music is just a very specific form of a much general phenomena that's constantly at play, which just comes to when things are doing the same thing at the same time, they can accomplish more, and they get in sync and out of sync. And when they're all in sync, then you get these resonant behaviors.
Well, I do have a varied history of adventures. Let me explain more about the experiment. So it's not just one experiment. I've done it maybe 1,000 times, maybe 100 different ways.
I want to hear how you're playing with gamma rays too. Please tell us about that.
How was I playing with gamma rays?
Yeah.
You send away for these little chips that have a radioisotope in it, and it costs $150. And then you somehow get the detector.
Do you end up on like a FBI watch list when you do this?
No, it's legal. It's they use it for testing Geiger counters and other tests. It's a check source. So there's a list of radioisotopes that you can just buy. And I picked the ones that we know have only one at a time emitted of gamma ray. And there are only a few of them. So part of the problem in this experiment is that there are only a few gamma rays that emit one at a time that have any lifetime, because a lot of them will just go away in some minute or second or something. And also, they have to have a high photoelectric effect efficiency for the kind of detector that I use. So there are reasons why this has not been noticed before amongst nuclear physicists. You have to know what to look for. And I did, because I figured out the theory ahead of time. So there are graphs of the photon energy versus the efficiency of the detector. Let's put a number here. And there are a few different ways, like the photoelectric effect efficiency will go down, and there are a few jumps in it. And then there's another thing. There's another effect called the Compton effect, where it makes a bunch of other little pulses that add up, and you don't really get to see this 2-for-1 effect if the Compton effect is dominant over the photoelectric effect. And then there's another thing that happens. And this is all different for different kinds of detectors. So the detectors are a crystal. The one that we use most is sodium iodide, and you put this crystal in front of a photomultiplier tube. So a gamma ray will come in, and it'll make a tiny flash of light, and then it'll make some billion number of visible H news that the photomultiplier will pick up and then make a pulse height out of it.
The crystal's like an amplifier of some sort?
Yeah, the photomultiplier, and then there's an amplifier afterwards.
Oh, I see. The crystal is just making a visible light for us to see.
That's right. It converts the gamma ray into something we can detect, which is a visible light flash that the photomultiplier picks up. Okay. So this is a very popular kind of detector, and I've used several other kinds of detectors, and I've made I call it the unquantum effect. If I get 2-for-1, where it goes to both, and I get a peak in the. Let me go back to the delta T graph. So there's time where if you see noise, it's just, if you get a peak in the delta T graph and you get a rate greater than chance, which is supposed to be impossible, I call it the unquantum effect. It's a 2-for-1 effect. I'm the only one that gets it or has any idea how to get it.
What's the rate at which you see it in both places? Like you said, I can see, what I do is compare to accidental chance. Mm-hmm. And I've seen all different numbers. Typically, it's 20 times chance. And chance is just 50-50?
No. Chance is by an equation that will equal just a random set of noise in this delta T.
I see.
At each of the coincidental detectors of this, and you just compare them.
Right.
Each coincidence will happen in time where this is left, right, this is right, left, or up, down. Let's call this left, right.
Are the pulses, by the way, those are measured, the pulses are before the coincidental machine? Like you compare pulses at each one of the coincidental counters?
The pulses come out, and then we put it into my fancy oscilloscope that can graph this.
Yeah, so you're measuring the pulses at the detectors.
Which are linked by this coincidental thingy.
The coincidental thingy being
we're
is that
looking
an
at
object or is that an idea?
It's an object, I think. It's a piece of it's an
well, they're
instrument.
They're linked together because they're. Are you still using this half silvered mirror, or what do you use to split the beam?
Usually, what I use is a thin detector in front of a thick detector. So a gamma ray will come through, and it'll make a click. It's supposed to be like a click here or there. So I'm doing the beam split in this thin, thick arrangement.
Mm.
Now I've done it where it looks like a beam splitter, but this works better, and I can get numbers up to several hundred times chance if I do it this way. So I'm splitting the beam in a series method, and so it's still, if you get it to go both ways and you get full height pulses, and that's really critical, and I'm very careful about that, because the pulse height is about the initial, what they call photon energy. And for the energies that I'm using, there's a number, it's like 88 keV, some number of electron volts of kinetic energy that each pulse should have. So we have and that's characteristic of the isotope that I'm using, which is usually it's cadmium 109 or cobalt 57. So there are isotopes that I typically use, and I've used several of them, that give out a gamma ray. The cobalt will be over here, cadmium will be over here, of pulse height. So
and these are just standard measurements. Like you can look this up in a textbook.
That's right. This is all standard from the textbook, where they know the kinetic energy, the numbers of KeVs. And so when you read a pulse on your oscilloscope and you see that most of the pulses are so big, and it's much narrower than the PMT. It's a narrow range of pulses, pulse heights. In this case, we're looking at a pulse height graph. So I set it here for the lower level. And what this lower level is much greater than the half height. So I'm not looking at half height pulses. People say, oh, maybe I'm looking at half pulse here and half a photon here and half. No, I'm not. I'm looking at full pulses, characteristic of the gamma ray known to come out of this isotope.
What is this? So when you set your thresholds, can you translate it back to kiloelectron volts?
Yeah.
Okay, so how many? So what threshold of keV is your detector set at? Like, where did you draw that line in terms of kiloelectron volts?
It's like minus 20% of the full kiloelectron volt.
Okay, so it's above 50%.
Yeah.
Are we still doing the coincidence counting?
We are. So that was the next question that I was going to ask, because I don't totally understand the design, which is thin in front of thick detector, and how that's the same as the beam split. Can you walk us through that?
I didn't know that we brought beam splitters into the coincidence counter before at all.
Well, it has to be, because what are you coincidenting, right?
That's right. Right.
The coincidence is, do you measure it at one beam?
Oh, I was thinking
location?
It was just a lamp that was going off in the center or something.
The coincidence is two detectors that are reading full height pulses.
They're beams. I didn't realize they were beams.
The beam split is happening in this direction, in this drawing. It's happening in series. I'm splitting off some of the energy here, and then some of the energy will still go here. So it's still a split in energy. So this detector is serving a dual purpose. It's serving the purpose of the beam splitter and a detector all in one. Now, I've done it where it looks like a beam splitter, okay? Where I had a detector behind here and another detector, and it split it. Mm-hmm. But I only get I might get 6 or 8 times chance. it won't be as sensational, but it's still sensational. Anything above chance is sensational. Nobody else has seen anything except noise like chance.
Well, I mean, it sounds like what you're saying is that you're getting like a 6 to 8x signal to noise ratio, which is pretty good. Like even in that configuration, you're still getting, if you're getting 8x above your noise floor, that's pretty good.
Right. I compare to the chance rate.
Yeah.
So I can get 8 times chance, 20 times chance, depending on how I set it up.
Sure.
But once it's set up, it always does the same thing. So there's all different geometries and spacings and detectors and there's a whole list of different ways I've done it.
And
to
those
make
two
sense out of it.
I've really got to make sure I understand this. So those two detectors each have their own pulse graph, which is then compared with this coincident meter thing?
That's a good question.
Yeah, there is a pulse height spectrum that I do for each detector, and it's even happening while I do the experiment. This instrument can read the pulse height distribution and the timing distribution, and even the shape of each pulse. All of that is recorded on the oscilloscope. This is a great oscilloscope that can do all that at once.
And the timing of the coincidental timing of that is compared against chance.
That's right.
Okay. So is there actually a machine that's a coincidometer or something, or is that just what we're saying to compound these nested
Well, I think it's the
it's the system.
It's the whole system,
Okay.
yeah.
I'm just
I like the coincidometer as a tool that you could go online to like Fisher Science and buy. But I don't think
there are people who've done some coincidence machines, but what I use typically are these nuclear instrumentation modules that are designed to do this kind of experiment. But it's like a rack of instruments that fit in to do the pulse heighting and the amplification.
And compare
so they're
them.
formal instruments that you can buy, but I buy them used.
How is the timing comparison being summed, I guess? Is that output separately, or how do you compare the coincidence versus chance?
I do it on my oscilloscope that has that capability.
Okay. So it can basically just add these two waveforms together or subtract or compare them somehow? It
looks at the timing in between pairs of pulses that will come in. Let me erase it.
I see.
There'll be pairs of pulses, and there'll be an oscilloscope trace. With one trace will have a pulse, and another that's for one channel, one detector, and the other detector, and it's able to read the time in between them, and then plot this.
Right, because the center point of that upper graph, which is voltage versus the delta T, the peak is at 0 delta T, which means that they are happening at the same time and not one after another.
Right.
Yeah, it's like almost like basic statistical modal comparison or something.
Yeah, exactly. Like I like this. I feel like I understand all of this.
Finally, thanks for being patient with this.
Yes.
I felt like a complete moron today, but I finally understand.
So there are people who've done this graph here, and the strange thing is there's one experiment that even sees a dip, and I call that out and say, look, that is an artifact of polarized beam splitters.
Now explain that to us.
If you have a source that's polarized and you have a way of splitting where the light goes, and the polarizers are typically polarized, it will bias, it'll route the light one way or the other depending on how it starts. Whether it's polarized up,
so basically the light has some sort of cohesive angular momentum to it, so it's going to deflect in one way versus the other.
That's right.
Cool. That makes sense.
Yeah. So that's one of the main artifacts I call out to these people and say, hey, you're using polarized beam splitters in your experiments and you're having polarized light. That's no good. Now, I don't hear anybody else doing that. I'm doing it. I'm calling out these people's experiments.
People don't like to be called out.
Yeah, nobody likes a critic.
I know. But
Better send chocolates.
Flowers.
That's part of what I do, is that I have to analyze many other people's experiments, figure out what's wrong. And also, there's a bunch of history where they just get it completely wrong in the textbooks to make everybody think that it has to be photons. There's a bunch of that I've done. And then there's a whole pile of experiments to say, well, this is not a special case where it worked with this isotope. I made it work with like 4 isotopes, 3 different kinds of detectors, different spacings.
You say there's no photons, but what is interesting is that these atoms, when they fill up to the threshold, they kick off a characteristic packet of effort. That's horribly reified way of putting it, but
that's okay. There's a characteristic frequency. It's frequency.
It's also energy too, right?
Yeah, you multiply by Planck's constant, you get energy.
But Planck's constant is a constant, which implies that there's a discrete amount of that energy.
I know. That's the illusion. Planck.
But
E equals h nu is correct.
It happens though, right? It's not totally an illusion, and so to call that phenomena a photon, even though it's radially emitted from the atom, it still has this discrete unit of effort, and that's what we mean by photon, I guess.
You could try to redefine the photon and say,
it might be easier, man, than trying to get rid of it, honestly.
Yeah, it might be, and that's sort of part of my problem. I'm saying it's more confusing to redefine the photon than to just get rid of it altogether. But if you want to redefine it, go ahead. There is something, there is a discontinuity in how light is emitted. It is initially emitted as a pulse of energy with energy h nu, but thereafter it goes everywhere. And there's also a discontinuity when it reaches the threshold in the absorber. So E equals h nu is correct on both ends, but this amount of energy is fleeting in my model, in the threshold model, because it has to go everywhere. Now, everybody else, they'll say that this thing that went everywhere is a probability wave. And then it determines the probability of where their particle will show up, whether it'll be wherever. And
this is just kind of a classic mistaking the map for the territory situation.
There are mistakes in history, and I can point out just what the mistakes are. The most glaring mistake, other than just thinking in terms of photons, where they did that plenty, but it's in all of our textbooks. They'll look at an experiment called the element of time in the photoelectric effect. And they'll try to say, well, they look at how many nanoseconds it takes for you to get some current. And they'll say, oh, well, it's only about 2-3 nanoseconds and then they'll say that's the only time. The textbooks will say that the photoelectric effect responds for no longer in response time than 3 nanoseconds. It's by Lawrence and Beams, and many of other people have done this experiment. Okay. But there's a mistake in understanding.
What's the significance in it happening in some discrete length of time?
If they say it happens only that quickly, then they'll say it acts like a photon. That's
because
part of
there's only enough energy inside of that time window to add up to a photon, essentially.
That's right.
Right
that's
on. Right. Okay.
But if you look at the data of the experiment, it's just not true. There's a whole bunch of other time that happened. But they don't tell you that in the textbooks. And it's even worse than that, because it's not just textbooks. It's very formal, famous physicists. And I have their books, and I can show you the page and everything, where they say right off that there's no accumulation time. And there is. There is an accumulation time in the experiments, and there's a way to understand this time and how it can load up. So there's some kind of weird I don't know if it's a conspiracy or stupidity, or they're all on the photon wave track or whatever to make them think this way, but they miss the point. And it's in so many books. However, there were some great people who understood the loading theory. When Millikan was examining it to try to see, well, was Einstein right about the photoelectric effect equation? He said, yeah, the equation is right. And he thought, well, how can that be that light is quantized? Millikan discussed in some detail, he called it the loading theory, which is the same thing that I call the threshold model.
Mm-hmm.
And your textbooks will call it the accumulation hypothesis. So in your textbooks, they will give, all the textbooks will do it. They'll give an example and say, let's calculate how long it'll take for the photoelectric effect to happen. And they'll say, oh, well, it comes out in so much energy and the atom is so big and everything, and you end up with like a minute. And then they'll say, oh, well, Lorentz and Beams found it was only a nanosecond. So therefore, it can't be a loading. You see, the textbooks teach you away from what I'm saying is happening. But they gave the wrong interpretation of the experiment. And that's only one case of where they screwed up history.
I'm sorry. How did you, maybe somebody can fill me in, how did they miss the first 3 nanoseconds of loading? Just threshold again of detection?
No, they're counting the first 3 nanoseconds.
They shouldn't be.
No, they're not counting the rest.
What happens if you count the rest?
Then you can understand that it accumulates. Then you get an accumulation time that you can reconcile with the example, the homework problem that they give you, and you can see that it can load up.
Let's unpack that. So basically, it sounds like what you're saying that in the way that it's presented, the students are taught that the photon is always measured in just the first 3 nanoseconds. But in reality, if you were to measure for longer, you would see more photons because it's accumulating.
You'd see other such clicks in their detectors, H-news. You'd see them happening with a longer accumulation time. More time would pass the response between the time when you emit the light and then you get the light. They're looking about, they had a really tricky way of seeing, well, how long does it take to go from here to there? And if it responds like only that quick, they'll say it has to be a photon. But what if it responds in 300 nanoseconds? Well, they don't say that, but the experiments show it.
That it does. So like basically, let me just make sure that, because again, this comes back to like experimental design. So you have some kind of source that has been treated so that there's one photon that's being sent out, and they look.
Actually, they don't need to have that. They could just have a pulse of light, but they're looking at how long it takes for the detector to respond.
And you're saying that the detector responds at 3 nanoseconds, but then if you keep looking at it, it'll respond again after a certain amount of time?
There'll be other such photon events that happen where it takes a longer time to respond.
From the same pulse of light?
No. Different pulses.
Different pulses. So you're basically going, you have some kind of emitter that you're letting light out from.
Yeah.
Like, how do you differentiate? So, like, how do you differentiate a pulse that's happening at 3 nanoseconds, 6 nanoseconds, right? Because if you have a continuous stream of light, and
it does. They make a classical pulse. It's bright. It's more than a photon's worth, but it's short. It's a short enough time that they can get these timings out of it.
I see. So they basically, it's a narrow enough window. So why would it take more than 3 nanoseconds for it to load to release a photon? What's actually happening?
The loading theory.
Well, like, is there a physical interpretation of that, or is
it's like the cups. It's the cups that I showed you.
What are they being loaded with? What is the photon?
The the light energy gets converted to kinetic energy of charge, and it takes time for it to accumulate to the threshold h nu.
Because there's some kind of inertia where it takes time to spin the atoms up.
It's just the nature of what electrons are in the first place.
Yeah, I mean, right. They're periodic structures.
Yeah.
That appear and disappear continually.
Yeah. No, I just want to get that on the table because I think that's the physical interpretation of what's actually happening. Because if you have, I think that the reason that quantum is so appealing to people, and we've said this on the show before, is that it's so spooky and weird and inexplicable and honestly lends itself to magical thinking. Because at the very bottom of things, you have some weird, spooky things that no one can really understand, and that's basically God. Full stop. Like, that's religion. And when you...
Something to pray to, anyway.
It is something to pray to, right? Like, I remember in high school, my physics teacher, when we were doing the quantum chapter, he was like, quantum theory says that if you take a tennis ball and you bounce it against the wall enough times, at some point everything will be in phase and the ball will go through. And I just remember being like, that's such bullshit.
Right.
But everybody's sitting around and is just like, wow. And
some kids in the corner like,
well, look,
yeah,
this is a big problem. It's about that the world is thought to be this kind of crazy, and I'm cleaning it up.
People don't like that. They want the lunacy. Like, people really love.
It's not going past me.
The buck stops here. Okay?
The buck stops here. That's right.
I mean,
that's exactly it. I'm the only one who has any kind of serious challenge. I have the serious challenge against quantum mechanics. I've had it since year 2002 or 3, and telling people about it. I'm just, it's been kind of nutty. I'm just pretty much ignored.
Let's talk about, can we hear a little bit about how you stumbled into this?
Yeah, because,
Well, I went to college. I did have 3 classes of quantum mechanics. So I have some idea of what they're talking about.
And did it bother you? Like, is that how you got into it?
Well, as soon as I saw the double slit experiment, I knew that it had to be the loading theory or the accumulation. I knew that what they were saying was wrong. But everybody said,
let's talk about interference and let's talk about that. But we can get to it in a second. I want to hear more about your story.
Yeah, making it.
It's very obvious that waves are going on, that there's interference effects. The problem has always been how to explain the particle property. And so that's the paradox. And that's those 2 parts of the definition of the photon that I did. The wave part is obvious.
In that there's some sort of like push-pull situation going on. There's some sort of frustration of these periodic structures that we call the atomic shells, that you don't get emission of light if those atoms are frustrated somehow. And these wave impulses are antagonistic.
There's a resonant absorption. You have to be in resonance or higher for there to be absorption. And so there's such a thing as a resonance absorption photoelectric effect.
And there must be there must be some phase relationship, right? Because what's happening when you scatter it off the edges of the slit is that you're getting misaligned phases in your reflections against the back.
That's straightforward wave theory, and the edges of the slits are not needed. You just need to know the size of the slit to explain all of the interference patterns. It's a very simple equation that's about the distance between the screen and the source and the separation of the slits. And
the slits are, you're right. You can do it with a single object. Obviously, you can get diffraction patterns just from one edge or something. It's not a problem. But it's still interacting with the matter that's in between, right? That the atoms are getting out of phase on their relay to the detector by the diffraction grating or the knife edge or whatever it is.
There are the forces of atoms at the edges of the slit are not needed at all.
Well, you have to have a slit, right? They're not going to
You
get
have
a diffraction.
you have geometry, you have the sizes of it. That's all you need.
But you're not going to get a diffraction pattern without something in the way.
Yeah, it's about the size of the slit.
Well, it's about the thing in the way that's doing something to the impulse.
It's about just how wide the slit is. That's all you need to understand the diffraction pattern.
Well, I think that the question that Shiloh's getting at is like, what is happening to the atoms in order to create the patterns of light and dark? Because the light is obviously a spooling up of the electron to activate the detector. And the dark seems like a spooling down of it in order to make it quieter so that it doesn't activate it.
It's very simple classical optics to understand the diffraction grating and how much energy shows up at the absorption screen. And so if there's less energy there, there'd be less.
Well, diffraction's a little weirder than that, because diffraction, you're actually casting shadows into the light, right? Which is really wild.
No, it's not a shadow pattern. Diffraction is not a simple shadow. It's about interference in two distances, and the waves interfere. So there are people I've called them out. Now, this business about diffracting, it happens with both light and matter. And it's important to know that I've done experiments with splitting the atom the same way, okay, which is like, wow, how did that ever happen? But I did it.
But hold on, before we get there. So you can make a diffraction pattern with just a knife, right?
Yeah.
So you don't need a slit at all to do it.
That's
actually.
Right. It's pure geometry and wave theory. You don't need to know the mass of the knife or any of that.
Yeah, but the question is like, what's happening? What is the knife?
I think what you're asking for is, what is the edge doing? Is that what you're asking?
Yeah, like what's going on here? You have a relay system, right? You have an atom on your detector, you have an atom on the knife, and you have an atom at the emitter. And then there's multiple photons going on, so there's multiple atoms involved. And there's somehow alternatively constructing the pattern at the back and deconstructing it based on their geometry, where they're located on the knife.
Yeah. All right, it's just really simple geometry of waves that's needed for this. If I could do it with a knife or a two slit or one slit, whatever, but the most famous example is two slits, and that it's about a difference in distance between the two slits,
right? That
makes it
out of phase.
Out of phase or into phase.
Right. So it's about the phase relationship.
Waves.
It's about, but waves of what? Waves of impulse upon the shells of the atom, right? And so the impulse
of classical electromagnetic field. I'm saying light is classical. It's not photons.
And so hold on. What this comes down to is a material conception for light. That's the point that you're trying.
That's what we're playing with right now. Yeah.
Well, that's the you haven't said that directly. So you have to put that directly.
Sorry, I was trained as a material scientist, so I'm always just looking at this in terms of material explanations for what's going on. That's why I keep talking about the shells of the atoms and so forth. So there's a phase of this impulse. It has a push and a relaxation phase to it. And when you get a relaxation signal coming into an atom and you get a push signal at the same time, it basically does nothing. And if you get two pushes at the same time, then you get a relay and it's transmitted to the back counter area. Otherwise,
it
they
makes
interfere.
More energy, but I'm saying it loads up still. That classical. So you could draw a graph of, let's say this is at the bottom. So you draw a graph of how much energy. And so this is going to be a node where there's no energy or hardly any. Here's where it interferes constructively, right in the middle. And so if you were to take a photomultiplier tube and scan it across here, you'll make this graph. But the paradox is, well, part of the paradox is that the photomultiplier tube will make these clicks, and they'll say, well, a photon hit there. Well, I'm getting around all that by saying, no, there are no photons. It's electromagnetic energy that loads up to a threshold, and and then all spills out and makes the click.
I totally follow you.
And I think that the reason that Shiloh doesn't want to get rid of the photon is because if you have to have something, some event, some object that's transmitting the impulse. Otherwise, you end up in this like very mathematical simulation world view where what's down there is the electromagnetic field, and the electromagnetic field is a set of changing vectors over time, rather than some kind of direct connection between different atoms that's actually transmitting the impulse. Because you haven't solved the question of how you transmit the impulse if you haven't answered...
The impulse has phase too, which is a really fascinating piece of this puzzle that I don't think should be ignored.
Like push versus pull.
It's either a pull or a relaxation. I mean, light has more of a push and gravity has more of a pull, but like there's some... I think it's fair to say there's more of a push and less of a push or something. Maybe they're opposite. I'm not sure.
Yeah.
But
I don't think that this is in any way, shape, or form against or antithetical to the threshold model.
No, not at all.
In any
I'm
way,
not
shape, or form.
criticizing anything.
This is a philosophical question, which we spend a lot of time talking about, but we don't get to talk about on the show too much, which is what is an electromagnetic field?
Right. Well, I embrace the electromagnetic field, and
It's very functional.
One step at a time. If we use the electromagnetic field in all of its classical glory, we can make progress. And I'm saying to do that, and also look at these timings, do the experiment without artifact, and just clear up this stuff about whether it's a particle of light or not. Do that first. And here we see, no, it's not a pre-packaged amount of energy that shows up, because that's the weirdness. Then the whole science turns into a circus.
Right.
Yeah, exactly. And so I think that what Shiloh is talking about is the one step beyond that, which is what is electromagnetic radiation? What is light? And that's
another question altogether.
Sure.
I'm not too worried about that yet.
Okay.
Yeah, that's something we do a lot of work
about
on.
How the speed of light. There are still questions about how does the speed of light work, and it's always measured the same thing and all that.
Yeah, I mean, for us that makes a lot of sense.
Calling that a separate problem.
It's totally one of our favorite problems, and so we see that speed of light as being the limit at which that material that connects the atoms can deform, and it deforms in a particular fashion, which has to do with the polarization of that momentum that we were talking about before.
Because if you go back and you look at the turn of the century, when they decided to get rid of the ether. They got rid of the ether because they couldn't detect it, right? There wasn't a substance that was the luminescent ether. There wasn't a substance that was between the atoms that they could detect.
That was distinct from the atoms.
That was distinct from the atoms. And so the next logical thing would be to say, well, then perhaps there is not a substance that is separate from the atoms where the atoms float in it, but what if the atoms themselves connect to one another through these thinned extensions? And
which are comprised of the same fiber as the atoms themselves.
Because if you look at the electron distribution, the radial distribution function of an electron, it falls off asymptotically with distance, which means that over a great enough distance, you still have a little bit of atomic material that's there. And if you have two atoms that are close enough together, then they would be connected through the extension of that distribution function, because we assume that the distribution function is a measurement of something that's actually there, not just some magic quantity of energy. Like there's actually there's an object between the two atoms.
They call them fields.
They do.
They do call them fields.
But a field is not quite the same thing, because a field is a time varying measurement, essentially.
It's an event that is in this material interconnection. And it's what this is not a new theory. This is literally just a physical interpretation of the equations, where you can say that the field is the way that this connection between the atoms changes.
The field's the behavior.
The field is the behavior, but the connection is there, and it is what is, to put it in the most...
But yeah, it becomes very easy to understand light at that point if it's a deformation of these thin filaments with different, twists to it that reflect the angular momentum or the polarization. And you can start to think of the deformation of any material has a characteristic speed. And so it should be no different with the thinned portions of the electron shell, which are responsible for light and gravity.
And then charge would be the movement of the shell. And so you can have the movement of the shell be greater or lesser and
have all sorts of complications.
But it's just like we've been building this model because we're like, look, whenever you talk to physicists, there's always this hard stop where people are like, there's a field, and then you're like, what is the field? And they're like, we don't do that. Like, it's fine. Like, we study above that. And so we found basically a gap where we're like, okay, well, we're interested in the material basis. And at some level, I really firmly believe that it's a philosophical question, because you have to ask somebody, hey, is there something there? Or is it just an idea that's down there?
I didn't think it was a problem where there's an electromagnetic field all over the place, there's a gravitational field all over the place. There is some kind of stuff there. It's just a field, and we can measure it and do all kinds of equations on it.
Yeah.
But to say, well, what's the nature of the field itself? Like, what is light like that? I'm saying one step at a time. Let's just see if it's quantized or not. Because a lot of these arguments that you're coming from is from this wave-particle paradox. I'm saying fix that first.
Well,
I don't think that we have any particles in our model at all.
Yeah, I think that
You
what
don't?
it is...
No.
The people talking to you do.
Of course.
Other people. Yeah.
But once you understand that a particle is just a particular crystallization of some dynamic function, like it's really just a photograph of a movie. And once you start to think about the movie being some sort of material in motion doing something, we're left with a system where there's essentially atoms made out of some sort of fiber, right? Because a fiber is different than a particle. A particle is just a mathematical point, essentially, that tells you some information. A fiber is some sort of material that has actual contours and has some surface which separates it from others. And so what we're saying is that the fiber, however heterogeneous or homogeneous it turns out to be, the fiber of the atom must be the same fiber as the connections which fill the voids which connect the atoms to their neighbors. And at that point, the deformation of the atom and the deformation of the filaments that connect them is easily it's easy to reconcile these speed limits and these impulses, and we can start thinking about what the waves are. Well, they're waves of pressure in this material, right? No different than any other phonon that travels in a material.
And it makes sense that it would be a thresholding event, because if you think of the way that a resonant object is pushed on, you have to sum that push over time in order to get a catastrophic event. I always think of the
Galloping Gertie,
the bridge in the Tacoma Narrows Bridge, right, where the resonance
that's the
shakes
threshold effect.
Exactly.
Right. But that's what I'm saying is going on with charge. The charge has these thresholds of where it'll emit and absorb. But light itself, that's the question I'm answering. Does light itself have anything quantized about it? And I'm showing no. No, that's an important step.
But the moment of emission is there's something the moment of emission is not necessarily quantized, but it is there's a discreteness there, right?
Like each shell can take each shape of the shell can take only so much impulse before it cracks into a new shape. And so there is something discrete to be learned about the configuration of the atom and the way that it shifts between these shells, these shell conformations, which we call energy states.
The input sums over time, but the output is a discrete shift.
Look, hear me out. I'm saying, how do you get a 2-for-1 effect? Can you do it with particles and waves? No. That's quantum mechanics breaks down. With this 2-for-1 effect, I'm saying, you have to see that there's some preloaded state there. It's loading up to a threshold. And then we make progress, understanding, well, what is light? It's not photon. There's something quantized in charge. And then how do we explain matter diffraction? Does matter have that effect also? Is matter always a particle guided by a probability wave? I'm answering that question with splitting the alpha wave. So I do an experiment with the same kind of setup with coincidences. It's a gold foil.
These are with alpha particles?
Yeah, the alpha particle.
This sounds like some borderline dangerous research, my friend.
Yeah.
Do you wear one of those like radiometers?
It's not that big a deal. You just buy something for $100 and you get.
No, I'm not
We're
saying
worried
that
about
you
you.
can't buy it. We're worried about you.
No,
We
it's
need
not
you
like
around
that.
for a
It's
long
so
time.
weak. It's like background radiation.
Okay.
I see.
You just don't eat it.
Okay.
So
You just wash your hands. Got it.
Okay, so alpha particles are thought to be matter, right? We can think of them as basically like
it's the helium nuclear wave function. It's helium.
It's
Or
helium.
heliumness. I like calling it's kind of nutty. I like calling it heliumness because if you call it helium, see just the words you're using, like the electron or helium, you're immediately put into wave particle duality. So I'm saying to be careful about the words.
It's the essence of helium.
It ends up being helium. But anyway, I use some radioisotope that puts out the alpha ray, and there's a thin layer of gold. And then there's my detector that's behind it, and another detector here. Okay. And so it's very similar to what Rutherford did for seeing this how gold splits. Usually it'll go through, it'll make a click on this alpha detector. Sometimes it'll reflect, it'll make a click here. Usually it goes to one or the other. Now, who would ever try to think that you could split the helium like a wave and show it can go both ways? I'm the only one to go do that. And I found that, what was it? It was like 6 times chance. It was sensational to see that.
So this is really, really interesting because we've talked a lot. So we've been working on this material version of quantum mechanics, and something that we haven't really gotten to is nuclear particles, like the nucleus. Like, what is the nucleus?
Well,
and the way
on a bit of this.
we've worked on it a little bit, but the way that I've always imagined it is that it is simply a resonance of the same material that the atom is already made of. Like, it's not actually, there's not like a little ball of something that's like a bowling ball that's magically floating around. If we're talking about a material that's in motion that creates the atom, and you have this standing wave, and if you break apart that standing wave, because it's not actually, it's not a discrete object, it's a pattern. Like the nuclear particles
you're
are
pretty
patterns.
close. You're pretty close. Let me outline a few other experiments because matter diffraction is old. And so electron diffraction, I think that was like 1924 or 5. 1930, Esterman and Stern, they diffracted helium also. And there are plenty of people who've shown the wave properties of matter waves, matter diffraction. But I'm doing it showing the wave property in an extra step. I'm showing where its particle property is defied to show that it has to be a wave. The quantum mechanics of the particle property of quantum mechanics will say that you're not going to get a 2-for-1 split here, but I did get a 2-for-1 split.
And I think that comes down to the ambiguity of what a particle is, right? Because if you start to ask quantum physicists what is a particle, you very quickly get to the point that it's not actually, it's drawn like a little bowling ball that's floating around.
Yeah.
But
right.
No one actually thinks that it's a bowling ball that's floating around.
That's because of this wave particle duality, and they know that it has wave properties and particle properties in different experiments. There's another experiment that I point out where they'll diffract helium in a set of slits where this is real interesting. They'll have a set of slits. It's actually concentric circles, and they'll have helium, and they'll look at the diffraction pattern, and there'll be this great big peak in the middle.
By the way,
And
are
then-
these matter rays? Can we think of them like cathode rays kind of setups?
Yeah.
Okay, so it's a vacuum tube with some very thinned out
Yes.
stuff in it. Okay.
Yes.
Okay.
Yeah. Yeah, they have
Okay,
an oven.
we
It's in
can-
a vacuum
I see.
chamber. That's right.
Oh, I see.
Now-
I see.
Now,
Yes, we'd have a.
what's interesting is that there's a particle signature where it'll go straight through, and there'll be a lot of clicks here that show it can go straight through. Okay, but in the middle, it has to focus. It has to go through multiple paths and do a diffraction pattern, interfere to make a pulse in the middle.
Mm-hmm.
So here we have an interesting experiment by somebody else, where they show the signature of the wave property and the particle property.
Mm-hmm.
And so that's an important clue. When you put together the message of my experiment and their experiment, the conclusion I come to is that atoms it's called solitons. A soliton has the ability to hold itself together or lose that ability and just spread like a wave. So we're able to see that. Now, in this experiment, I
guess I would interpret it a little bit differently, but I think that it comes down to how you treat ions inside of this vacuum chamber, because the way I would see it is that the atoms which are ionized are essentially ripped open to begin with. They're stretched open because they have a different set of pressures than they would under other conditions. And this allows them to, in very rare conditions, to be in contact with one another such that they conduct a current across that distance. And so as you have these lightning bolts, essentially, of atoms interacting across both of the slits, that their angular momentums are going to interfere and construct depending on their geometry with respect to that reflection that they must undergo. And so you'll end up with this pattern of thresholded events, whatever you determine is your threshold, and you will see that the atoms are alternately fighting each other and constructing to give off detections at the back surface.
And it still comes down to it not being a particulate
for sure.
model,
For sure.
right? Like, it doesn't make sense to look at it in a particulate model, no matter what.
This part of the experiment, right, it's not a particle, but here it goes straight through. There's no diffraction needed. So you see both signatures.
Right. Yeah, I think that's commensurate with the way that I'm looking at this.
But this can still be explained with the probability interpretation.
Of course, yeah.
Well, but that's where my experiment comes in.
Okay.
My experiment of splitting helium like a wave is against the probability interpretation.
I see.
The probability interpretation will say it only will go one way or the other. You see, the beam split experiment is a far better explanation of the weirdness of quantum mechanics than the double slit. The double slit experiment is halfway kind of saying, oh, there's wave properties and particle properties. The beam split experiment, it really gets to the heart of the problem, where if it was to go to one way, it eliminates like a form of entanglement the other way. And so you get the weirdness of quantum mechanics to say, oh, the wave function collapsed to go here. And then you say, well, how does that happen? It's called the measurement problem. And they know it's a problem. It's weird. But I'm saying, no, it doesn't always happen that way. You can understand to make the experiment, to make it go both ways, there is no collapse of the wave function. We can correct quantum mechanics, and we can do a different interpretation of a whole pile of equations.
Yeah.
Now, there's some detail of my theory that I'd like to get to explain how can it be that matter can go smearing out like a wave. What the hell is going on with that? Well, I have an answer for that. And it's about looking at the constants in our equations. I'll try to do it like for the electron. So let's look at the de Broglie equation. like wavelength is equal to Planck's constant over mass times velocity. So with that, they put it on the electron diffraction experiment and also this helium diffraction experiment. It conforms to the de Broglie equation. And so we can see about the velocity and the masses of the helium and everything, or electrons, or whatever we put in here. So we have equations that have ratios. This ratio. Now, if you look at the photoelectric effect, and there's a list of experiments that I've noticed this beautiful symmetry of. This is my theory as to how does all this happen, make sense out of it. There's the photoelectric effect has it has a charge to mass ratio in it as part of the equation. There's the Compton effect, which has the H to M ratio in it, and there's the Lorentz force, which has the charge to mass ratio in it. And there's another force, the Arnav-Bohm equation, that has an E to M. So we have these constants in our equations. Now, people always look at these as if, like, Planck's constant is thought to be just about quantization. But there's this trick I'm using where it's a threshold, and that Planck's constant is really about a maximum. So what I've done is I've taken these other two constants, E and M, saying they are also thresholds. But you don't see it in the experiments that show wave properties. This is the most important thing. This is what I did first to realize that the experiment would work. Because it's the ratio in these experiments that's quantized, not the individual E or the individual M. So it means you can have less charge and less M in the wave that's smearing all over the place, but there's a property of the wave that's conserved. And that's the ratio of these properties, the charge to mass or the action to mass ratio. There's three ratios. I call it the ratio trick. And so if you look at some piece of spreading matter wave, like, what is this helium wave that's smearing all over the place? Is it really a wave? How does it transmit what it's doing? If you take any piece of this wave that's characteristic, you'll be able to picture in the equations like the de Broglie equation and look up, well, what is the H to M ratio of this piece of the wave? And interpret it in terms of a wave where this is conserved, but the individual action in this volume of space and the mass in this volume of space could be much less. It's not quantized. It's not at the threshold. It's the ratio that's quantized. So this is going to take a little time to get your head around, but that's where I'm coming from as explaining how can it be that matter diffracts and still transmits what it's about. Mm-hmm. It's this trick.
Yeah, I mean, again, like I said, I see it more as a product of the geometry of the setup coupled to the thresholded feature of the detector, where the atoms are relaying across these different surfaces impulses that are out of phase and in phase with one another. Alternatively, it's not like the atoms doing anything spooky or crazy. It's just that they're lined up and transmitting impulse across different distances at different phase relationships.
Look, you're going to see wave effects. When Esterman and Stern diffracted helium, they had to use the de Broglie equation to say, well, they saw that it satisfied it. And you're immediately confronted with paradox. How can it be that a wave made an interference pattern? But this is a way to see through the paradox, that the ratios describing this matter wave are conserved. And so the easier way to do it is with charge, the charge to mass ratio, to understand electron diffraction first. That's the easier way to understand it. So just look at the experiments, I'm saying. What experiments show wave effects? Well, it wasn't quite like a dual slit experiment. It was like a wire, and it went around the wire, but it was like two paths, and they could see charge diffraction. And, G.P. Thompson was one of the first people to do it, where he bounced J.J.'s son.
J.J.'s son, wow.
Yeah.
Cool.
J.J. is famous for the particle interpretation of charge, and his son showed the wave version of charge by diffracting electrons off of or through thin foils.
Right.
And Davidson and Germer did it by reflecting charge off of the surface of a crystal about the same time.
I guess I'm just saying, like, to me, the magic is happening at the diffraction site or at the reflection site or whatever. And that's when the phase relationship is getting messed up between the source of the impulse, which is downstream in this ionized column of shells which are interacting with one another. And it's getting out of phase at this interactive point, which is causing it to create a relayed out of phase relationship with the detector.
That's true. That's right. That's the same thing I was doing with the double slit experiment, where there's a different distance.
Yeah, exactly.
From the two slits. Well, this is just the crystal lattice instead.
Right. I think it's telling you less about the shape of the atom or the construction of the atom than it is about the way that the electric impulse is being conducted in this geometric fashion throughout the landscape of the test experimental effort.
It's important to understand the nature of charge. These experiments point out a clue. And so the trick about physics is to look at all the experiments and get a consistent model. Quantum mechanics has a crammed together wave to particle kind of, it's not a consistent model. I'm showing there's a way to have a consistent model removing wave particle duality.
Right on.
So it's not just me talking. It's about, I'm saying, do the experiment. I'm asking somebody else to repeat my experiments.
Well, hopefully someone will hear this and get to it. Is it pretty cheap to pull these experiments off, by the way? Or like, is it something somebody could get into at home?
How much is that oscilloscope?
Well,
do you need that fancy? Yeah,
that's not too bad.
It's about $1,000. So it is, as experiments go, it's an easy experiment, especially with all the literature that I put on my website to say all the ways to do it. It's easy.
That's cool.
Definitely.
Yeah,
do you share all of your data so folks can play with it?
There are no secrets. I put everything down.
Nice.
And some of the best writing were my patent applications, where I put some detail in there. But yeah, all the detail of my experiments are on my website. I do have one student who has been putting together a way to reproduce my experiment, but I don't know why he's taking so long.
Funding.
What was that?
Funding. It's the funding crisis.
No, he doesn't have a funding crisis.
Okay.
I sent him a bunch of stuff.
He's a rich baron.
Yeah. I mean,
cool. Well, yeah, I hope people will go and check out your research and start to reproduce it. I do think it's all very consistent with the way that I'm looking at these experiments. I hadn't been aware of any experimental
confirmation of a different worldview. I mean, I think that this is the way that science has always been done, and for the last almost 100 years, maybe a little bit less, science has become much more of an engineering process than it is a scientific one, where the goal is to create models that then allow you to make a computer, a bomb, the medical machine, whatever it is.
Yeah, as long as your clicker thingies work, then people are kind of like, who cares whether it's a particle or a wave? Like we can engineer.
I've talked with some engineers about this idea that the semiconductor industry came about because of quantum mechanics, and they were right there, and they said, no, it's not like that. And that a whole bunch was done empirically, and then later you can explain it with quantum mechanics.
Right. Yeah, people don't understand how much just smashing things together, trial and error, it is working in an engineering situation.
And I've always thought that the way that you can move these ideas into wider acceptance, like anytime that anybody has an idea where they're like, look, the scientific interpretation of whatever experiment is incorrect, I have a better one. I think that the proof is in the pudding. Like, you have to be able to build something from your new understanding that people couldn't build otherwise. Or you have to be able to predict that they're going to be able to build something according to your interpretation down the line. Because if as soon as your idea becomes useful for engineering something that people can't figure out, that's when they'll switch to that model, because the model is what is used to build things. And literally no physics department in the entire world is occupied with, hey, are our models correct? They're working with models that let them build stuff. And if you can come up with a model that helps them build something new or something cool or something crazy, they'll use that model, but it has to be instrumentalized. Without that, you just have people being like, who cares?
Well, I know. That's why I'm an experimentalist.
Yeah.
I had to find, and I did make quite an effort to reduce to practice in photon violation spectroscopy, where I was able to see properties of matter and how electrons jiggle around that nobody else can see. And so I sent that to the patent office thinking, wow, that should be all right. But they treated me like garbage for both patent applications, also for particle violation spectroscopy. So yeah, there are practical ways to see it, but I've only gone so far. I've not figured out how to make my flying saucer run on quantum effect yet.
Right? I mean, and that's the tragedy of it, because like that might still be 100 years from now. And the ideas are already here. And science is such a process of iterative discovery that back in the day, when you had people just writing stuff to the Royal Society and nobody had these preconceived notions, like I was looking recently into the discovery of electricity, and there's literally a letter that Samuel Gray sends to the Royal Society where he discovers that you can communicate electricity. And the way that they're working is that they have these glass tubes that they're rubbing to get static electricity on them. And it sounds insane, but what he's doing is he's taking any metal object in his house and suspending it on silk lines from the ceiling, and then showing that at the end of this chain of metal hanging things, you can still attract a pile of chaff to the end of it. And he's sending it to the Royal Society, and people are looking at it, and they're like, oh, that's quite fascinating. And then they're like, somebody else and goes, and they repeat the experiment, and they're like, oh, that's quite fascinating. And then somebody else goes and builds on it. And it's this foment of curiosity and discovery, because no one understands what electricity is, and nobody purports to understand it, because this is 1731, right? And we're now at a time where people are like, no, we have this. We understand it. It's done. It's zipped up. Look at our cell phones. And so there's not this, the ability to do this kind of experiment is squarely outside of the academy, because the academy has focused in on the fact that they understand, and they do understand well enough to be able to build something. And so it's only people like you that are operating on the outskirts with time and interest that are able to actually push the frontier forward. And so it's very, very cool. And I'm sure that it must be very frustrating how alone you are at that space.
Right. I did this 22 years ago.
And
I've been telling everyone ever since.
Like, one of the hopes of Demystify Psi as a project is that we create an institution where people like you can come together and they can start to collaborate again, and they can start to build on each other's ideas. That's really, I want to be able to have, the Royal Society of the 1700s here, where people are coming up with things and they're showing things that are unusual and weird and strange and telling each other about it and then going out and exploring it further because that's the only way that this stuff is going to move.
Well, the thing about my message is compare it to conventional physics and say, well, which one is weirder?
That's true.
They're going through all these acts of desperation. I call it, for multiple universes and holographic, and everything's connected across this. It's just too nutty. So we don't need any of that. And there's a simple answer. And the scientists in the early part of 20th century, they actually did have an alternative. Like the people I mentioned, Planck's second theory of 1911, he was really on the right track. He was able to take his black body spectrum that everybody says has to be quantized energy. He was able to show in a derivation of the same equation, the black body distribution equation, that Planck's constant can be thresholded. And so it's called continuous absorption, explosive emission. And there's a good book on it by Thomas Kuhn, who's famous for the paradigm, what's it called?
Paradigm shows.
Yeah, so he wrote this earlier book about Planck for the most part. It explains the threshold model that he was working on and all the contortions of it. And then
we're going to have to get that one out of the library.
Yeah. And so I've been looking up all these papers. I have, you can't see it in my video, but I have a whole wall full of books and papers that it took to track down, well, what's going on here? And about what, so
you look like you live in a library. I love it.
Well, half of it is a library. The other half.
Yeah, there's the real gear.
Right, that's the gear.
This is a beautiful little space you've got there.
Oh, it's unique, all right. Let me see if I can get.
That's really cool. I was kind of hoping you were going to show us one of these experiments in real time, but
well, I could at another session. It's possible. I can set up the camera in front of the oscilloscope. I could show you those pulses. The way they come in.
Maybe we could do like a short little video for the Material World channel too.
We're gonna be in the San Francisco area in like a month or two.
Hey, maybe we could just film something.
Yeah, maybe we
come and visit. Come and visit.
All right.
We'd love
to. Now I do not have.
Can we get you back on the screen? There you
go. I do not have the radioisotope. They wear out. They only last about a year.
I'm fine with that.
Right. So I don't quite have the ability to run the actual experiment, but I could show you how the clicks in the oscilloscope and the other electronics work and the detectors work. Unless I just go by this isotope, whatever. So there's a lot to see here as far as all the instrumentation. And I could show you the next experiment I'm working on. So having resolve what I think is the secret of physics, I'm applying it to figure out, well, what is life about? I'm working on a secret of life project.
Oh, yes. That's what we've been doing all week long.
Right.
Yeah.
So,
by the way, do you have a definition for life? I ask everybody.
Well.
I hate to put you on the spot with that. I'm sorry. We've had several podcasts this week.
We came across a very, very cool one this week, which is life is that which can create complex molecules.
Which is a threshold.
Model. Yeah, exactly. Because there's a guy named Lee Cronin who's an organic chemist at Glasgow University, and we had him on the pod. We recorded, but we haven't released it yet. And he is trying to evolve life de novo in the laboratory. And in order to do so, he had to come up with a definition that he could use to evaluate whether or not he had succeeded. And he basically looks out onto the world and he's like, look, there are chemicals that cannot be produced without the machinery of life because they're too complex to be made with random reactions. And it has to do with the number of synthesis steps that are required to produce something of that size.
He's like, look, if you have something that's above a certain atomic unit weight, it's got to be made by light.
Complexity.
Yeah, it's thresholded complexity. That's quite fascinating.
That's right. Well, I'm working on it.
Cool.
I'm doing a combination of frequencies approach. I'm using tuned microwaves in a bunch of secret ways to see if I can change the rate of reactions in photosynthesis. And I'm able to monitor that with chlorophyll fluorescence. So I'm trying to influence the rate of chlorophyll fluorescence with tuned microwaves. And so I'm trying to invent a spectroscopy to find the tunings in a part of the spectrum that we have some handle on, like microwaves, to where we can send it in and affect, let's say, an enzyme reaction to go faster or slower. And then once that's developed, it'll eventually be for electromagnetic medicine and also for figuring out how life works. So
that's awesome.
I can show you all that if you want to come over.
Yeah.
Yeah.
That sounds
I'd love
amazing.
to take you up on that.
Yeah.
Yeah, let's
put a pin in it. I mean, this has been amazing.
Yeah, you have a really cool stuff. You have an awesome life over there. It's I'm really impressed that you're just slaving away in isolation like this.
That's right. That's right.
Well, I'm glad you must enjoy it. You seem like a happy fellow. So, stay inspired and keep at it. This is exciting.
So there are all these details that I've been kind of going over fast. They're all on my website. The better parts of my website are my lecture slides, where each of these pictures that I do in detail, and there's references behind it. And so there are two good lectures. One of them is on the experiment, all the different ways I do the experiment. And the other lecture is a critical history of quantum mechanics and wave-particle duality to show, well, just what happened in history where it could be interpreted by this threshold model, and they didn't see it, or they decided to go a different way, and what happened. And so that's an important part of my message, is that there's a way to look at very important parts of the history of quantum mechanics to see it does not have to be the way they say in our textbook. The textbooks are so emphatic in insisting that they're right about it, and they are so wrong.
Well, that's because, again, training of undergraduate science students is not about creating scientists. It's about creating engineers. It's about making people who are going to know the rules and be able to go and work at like the Apple, Facebook, IBMs, and make stuff. I
don't know. There's some kind of momentum of thought that has gone astray. Absolutely. And this business of giving the Nobel Prize to these people who try to say that the universe is crazy was the most disturbing thing that's happened ever.
There's something like strangely unsurprising about the postmodern approach to nothing can make sense being lauded in our modern society.
You guys, people need gods, and the minute that you're like everything is explainable and rational in the material world, you take away God, you take away magic, and that's the thing that I think that you come up against, which is that people are really attached to these ideas in a way that seems irrational, because you put it down in front of them and you're like, hey, this is a better way of seeing it, but you take away the magic. And
there are many people who have alternative theories to quantum mechanics and all kinds of ideas about it, interpretations of it, and there are many people like that. They do not have an experiment the way I do.
Yeah.
I'm the only one that has the experiment to show where quantum mechanics fails. And I have it in great detail. And I'm sure to be hit with all kinds of people saying, oh, well, did you measure this background radiation or this other thing or the whatever effect? Yeah, I've been through that, all the different ways. job of an experimental physicist is to figure out how you did something wrong and see if it still holds up. And so you could see that in my papers that I've looked at these sources of artifact.
Nice. Yeah, as you should. And I'm sure that as people start to repeat these things, I mean, that's the thing. You can't really keep some apparent phenomena hidden away forever. It's like...
You can for thousands of years.
Yeah, you can, but not forever.
Yeah.
You know, eventually people start doing it themselves, and
eventually the
cat's out of the bag.
Earth is no longer at the center of the universe. Like, it does happen. It is, again, I think it's a threshold transition. This is, you have to put a lot of effort and a lot of time, and a lot of people have to pour themselves into the question before there's a titanic shift. But it will shift. It absolutely will shift.
Yeah, after I'm dead.
It might be, maybe after we're all
It's all
dead,
part of
you
the
know?
game, my friend.
Yeah.
It's all part of the game.
Yeah. I hope
The
it
project is
shifts.
bigger than us.
The project is bigger than us, but I always do hope that it will change within people's lifetimes, because it just...
I mean, considering how much has changed in our lifetime, I would not rule it out.
Yeah, I mean, like, I love the feeling of being right, and so I always wish it upon people that are working hard at stuff. That, like, I hope that you see the day that you are vindicated.
Thank you.
Exactly.